Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 2, part of this playlist, which I'm calling Discrete Random Variables. And today's topic is the binomial distribution. Now, a little bit of development before we jump into it. Let xi, I equals 1 to n, for a given n, be a sequence of Bernoulli trials with parameter p. So remember, xi takes on the values 0 and 1. Each xi has a Bernoulli density, which we covered in the last video, the previous video to this one. Now let's assume we want to know how many successes out of n trials were observed. Call that x. So we're going to add up the Bernoulli trials, right? Each of these is a 0 or 1, and adding them tells us how many successes. Now assume there are little x successes out of n independent Bernoulli trials. So for each given sequence, so we know the sequence of zeros and ones. The probability of that it equals x given that specific sequence is p to the x, right? There's x successes and there's n minus x failures. However, before the Bernoulli trials are observed, what's the probability of observing x, little x successes? So each given sequence has the same probability, but there are n choose x different combinations or different ways to have x successes. You can move those zeros and ones around and still have x successes. So this is the probability. And this is what we call a binomial distribution. And that's the topic of today's video. So let x be a binomial random variable with parameters p and n. Then f of x, given by this, is a density. That means that you sum it over all possible values and it equals 1. Some may call it a probability mass function, but this is the density of the discrete type, so both are okay to say. The proof uses the binomial theorem, which we're going to use a few times in this video, and it's actually something worth having in your mathematical tool bag. So f of x, that should be the sum of f of x, is equal to this, right? F of x is just this piece, and then we're summing them, so I need a sum. But this equal sign, use the binomial theorem. If we just call p the variable a and 1 minus p b, then a plus b raised to the nth is this sum. And I have a video called Binomial Theorem if you want to see that proof. But p plus 1 minus p is just 1. 1 to the nth is 1. And so it is a density. And again, I need this summation sign out front. I'll correct it in the hard copy. Let x be a binomial random variable with parameters p and n. The mean x is given by n times p. Here's a proof. So let x, expected value of x is x times the density summed over all possible values. So we plug in the density. I just moved in x here. And when we, so one of these p's, I move out front. So that's what this is. So we get p to the x minus 1. When you write out what this is, you get n factorial. So I take one of those n's and put it here, and we just get n minus 1 factorial. Now also notice when we sum x equals 0, this term is 0. So we might as well just start at 1. And then here we get an x factorial, but one of those cancels with this x, leaving x minus 1. Now if we do a index change, y equals x minus 1, so this becomes y, x becomes y plus 1, and we're summing from 0 to 1, and then this use the binomial theorem again, where this is a and this is b, but we're only going for 0 to n minus 1, but 1 raised to that power is just 1, so it's n times p, and it is proven. Now a second proof, let x equal x1, x2 to xn, where xi are a sequence of independent Bernoulli trials. This is the way we thought about it in our development. So the expected value of x is equal to the expected value of this sum, which is the sum of the expected values, but each of these on a Bernoulli trial is p, and then we get n of them, and that's n times p. Let x be a binomial random variable with parameters p and n. Then the variance is given by this expression. It's NP, and then a lot of people call that Q. It's 1 minus P. So let X equal, X1 through Xn, where Xi are a sequence of independent Bernoulli random trials. The variance of X is equal to the variance of this sum, and since they're independent, it's the sum of the variances. But the variance of a Bernoulli we learned in the previous video is P 1 minus P, and we get N of them, so that's NPQ, and that's what we wanted to show. Let X be a binomial random variable with parameters P and N. The moment generating function of X is given by this. It's M of T is the expected value of e to the tx, which is this, P e to the t plus Q raised to the N. So proof number one is, by definition, its expected value of e to the t. So that says put e to the t times the density, sum to overall possible values. But let's move this e to the tx in with px. And that's what we do here. But using the binomial theorem, where this, comes here and this term goes here, and it's raised to the nth power, and boom, we're done. So that's another usage of the binomial theorem. Now, a second example of a proof, let X equal, X1 to Xn, where Xi are the sequence of independent Bernoulli trials. We're going to use Theorem 6 from video ims19, and this stands for, it's the 15th video in the playlist Introduction to Mathematical Statistics, which ends up being the moment generating function video. So M of T is expected value e to the tx, but since X can be thought of as a sum of independent random variables, that's just the product of the moment generating functions of the Xi's, but the moment generating function of these Bernoullis was P e to the t plus Q, but we're taking it times itself in time, so it's raised to the nth power. And that's what we wanted to show. Now here's an example. A person flips 2 coins. Person B flips 3 coins. The winner has more heads. If a tie, repeat until a winner. Find the probability that person A wins. So we're going to let X equal the number of heads from A. And X is a binomial random variable with N equal 2 and P equal 1/2. Y equal the number of heads from B. And Y would be a binomial random variable with N 3, right? We're flipping 3 coins with P equal 1/2. Now let's let T equal the number of trials for a given, so, so if we flip at 1, A and B flip their coins, that's trial, or T equal 1. If it's a tie, we go to T equal 2. If it's a tie again, we go to T equal 3. Now for any given trial, right, because each trial is independent. So on trial 1, everybody flips their coins, and if we tied, the results on the next trial are independent of what happened before. And so on any given trial, the probability that X is greater than Y, so the probability that A wins, is probably that X is 2 and Y is 1, right? So A flips 2 heads, person B flips 1 head, or that X equal 2, Y equals 0, X equal 1, Y equals 0. Since X and Y are independent of each other, and it ends up being the product of these two probabilities, but these each have a binomial distribution. X is a binomial random variable, so we can plug it into the binomial density. N is 2, X is 2. P is 1/2 raised to the X, which is 2, 1 minus P, 2 to the 2. And then for P equal, Y equal 1, we plug it in, 3 choose 1, 1/2 to the third, 1 minus P, 3 to the 1/2. And then we do that for each of these in there, right? Because each of those are just binomial random variables. We can crunch the numbers, and the answer is 3/16. On any given trial, the probability that A wins is 3 out of 16. Now, the probability that X equals Y, so we have a tie. That's probability that X is 2 and Y is 2, or x is 1 and y is 1, or x is 0 and y is 0. And since those are binomial random variables, we can plug them into the densities and we get these. And I would recommend you do that on your own to make sure that you can come up with these. And the answer is 5/16. So now we can look at the probability that A wins. And this is, it's the probability that A wins and he wins on trial 1, plus the probability that A wins and it's on trial 2. Probability A wins and it's on trial 3. It's the sum of these individual probabilities for each trial. But we can use conditional probability, and it's the sum from 1 to infinity, that the probability that F is I, so that we're on trial I, and the probability that A wins given that F is I. But remember, on any given trial, it's the same probability. So this probability that A wins on any trial is 3/16. Now we have to look at the probability that we're on trial I. Now to be on trial I, that means we had to have tied on the previous I-1 trials. So that's 5/16 raised to the I-1. That's the probability of tying on each of those previous trials. Well, the 3/16 is not indexed, so it can come out front. This is a geometric series, has a definite limit. Take this product, it's 3/16, which is 27% chance that A wins this little game. Now this is what's, we're going to simulate it. We're flipping coins. So as we go down this, roll is 1. We automatically roll once, and we're going to continue unless there's a winner. So we let A flip. It's a random, we take a random binomial distribution. We want one observation, n is 2, p is 1/2, right? So this takes on values 0, 1, and 2. That tells us how many heads that A flipped. B is a random variable, a random binomial distribution. We want one observation, n is 3, p is 1/2. So since n is 3, this can take on values 0, 1, 2, and 3. Now if A is bigger than B, A wins. If B is bigger than A, B wins. Else continue. We just keep flipping. So the next we add a roll count to our number. A and B flip. We check the results. If it's a tie, we keep going. We're going to put out the roll number, how many rolls we did, and the winner. So let's run this. Flip coins. It looks like we rolled once and B won. We flip again. It took 2 rolls and A won. But now let's do this a simulation of 500,000 different times. So we use sapply from 1 to 500,000, and we're going to run this function flip coins. We're going to store the results and flip. Remember, the output is 2 pieces. It's roll number and winner. So let's look at the mean number of rolls for this game. It's almost 1.5 rolls. So it's usually 1 in 1 roll, but sometimes it goes to 2. Of course, it can go on also. But the probability, let's just table the results. A wins, B wins, and then look at the proportion of each. And it's 27% that A wins, which is exactly what we got in our theoretical development. Okay, the next video will be negative binomial, and this is all I have for this video. Hopefully you enjoyed that. As always, I'll put the R code in the comment section for you to copy and paste into your program. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.